Started. Let's get started. So the last time we were looking at the discussion on the motion control systems, and we were looking at the idea of successive loop closure, and we were looking at the idea that how do we place the poles of a system at a prescribed location that we want to fix them at, and we looked at some mathematics regarding it, but we really wanted to apply that to the Nomuto model, or at least some ship dynamics model today, in order to see where we were. So before I do that, maybe we'll head back there one more time, just so that we are sure on some of the concepts which were not very clear last time. Okay, so the idea here is that instead of having a single feedback loop, I want to have multiple feedback loops which can help me make my control system relatively simpler and not as complex when I'm looking at a single feedback loop around the plant. And sometimes you will actually see that this second control loop can be a part of the so-called guidance system. That second closure is not actually happening as a part of the control system, but might be happening as a part of the guidance system. And we'll take an example today. We'll try to see where that happens so that we can get a sense of what is going on. So given that I have two plants, so the plant is given by P2 times P1. And then we are looking at if we want to close the inner loop control law in using a controller C1, such that U1 is given as C1 times the error between Y1 and R1, where Y1 is the output of plant P1 and R1 is the reference signal that I want this inside control loop to track. So I'm going to take the difference between R1 and Y1, which is going to be given by my E1, feed that through my controller in order to get the output, which will be U1. And that U1 is now applied to the plant P1 so that Y1 now keeps tracking R1. Everybody with me so far on that? Okay. All right. Now the idea is, once this inside control loop has been set up properly, we will assume that Y1 is almost equal to R1. So it is as if this entire loop has disappeared and I have a straight line connecting between this control point. C2 output gets directly connected to the P2's input, right? If I have tuned my controller properly, and if Y1 is almost equal to R1, I can say that I can tune the outside loop independent of the inside loop. And that's what we try to do, okay? So as long as this transfer function between Y1 and R1 is approximately 1, we can tune the outside loop independent of the inner loop. Again, we go through the same process and we find out that the outside loop's transfer function between Y2 and R2. So let me go back here. Y2 is the output of plant P2 and R2 is the reference signal that I want Y2 to track. Okay, so if I observe what is the closed loop dynamics between Y2 and R2, I can write that down as P2 times C2 divided by 1 plus P2 times C2. And the idea is that if we want to make sure that this cascade of loops is stable enough, we want to ensure that there is sufficient bandwidth separation between the inner and the outer feedback loops. And we typically want the bandwidth of the outer loop to be smaller than the bandwidth of the inner loop, so that the tracking can happen perfectly. A typical value of W will be 5 to 10, which means about 1/5 to 1/10 bandwidth you expect in the outer loop as compared to the inner loop. We try to take also an understanding about what is this pole placement algorithm in the last class, and where we looked at a second order system. So if I am given a second order system and that is being applied some control law, where we are assuming that the desired value of the output is actually a set point, which means yd is not a function of time, or yd of t is yd that's equal to constant. And that ensures that yd dot is equal to yd double dot, and all of those are equal to 0. That is the main idea. In which case, I can write my controller's input, the control input, as minus kp times the error minus kd times y dot, where the error is defined as y minus y desired. By putting this control in, we observe that the system's closed loop dynamics now becomes given by the system here. And we actually tried to derive this in class yesterday. I had the exercise given to you guys to try to see if you can arrive at it. Now, the idea here is that typically these control gains which are there, Kp and Kd. So it's occurring here, here, and here. These are the gains that we can control, and then we can see how well the desired trajectory is actually followed by the actual trajectory, right? So the actual value should follow the desired value as closely as possible, and that can be tuned by changing these gains. Now, the idea is here that this transfer function which we have, we can basically control where its poles are located. Okay, the idea is in the complex S plane, we can specify where the poles of the system should be, and then accordingly figure out what should be Kp and Kd so that a desired behavior is observed. The location of the poles really determines how the response looks like, and if the poles are all in the left half plane, we know that the system is stable, but if we have any poles in the right half plane, we know that the system will be unstable. Everybody with me so far on this? Yes, okay. All right, so now the idea here is that yes, these gains can be tuned and we can kind of keep increasing them until but in a practical scenario, we want to make sure that these gains are not representing some unphysical inputs. So I should not be saying I need to run my RPM at 10,000 RPM, which possibly cannot be achieved, let's say, by our actuators. So that doesn't have any meaning. So therefore, we have to make bounds on these gains, and that for achieving those bounds on the gains, we typically want to figure out what is the maximum value of U that we can look at, and we try to specify our proportional gain as this maximum value of U divided by some tunable parameter EY or max. So as I keep tuning EY max, I'll specifically be getting my proportional controller gain, but at the same time, when y dot is equal to 0, so in the steady state case, it ensures the fact that my U does not exceed U max. So we are kind of making sure that our controller gains are tuned using design parameters such that we are not seeing them go beyond certain practical limiting values. And that is why we introduce these parameters. Otherwise, I could have simply said that I'll choose Kp to be my liking. We are not doing that, and we are specifying it in terms of U max, specifically so that the control input doesn't ever go beyond that value, more or less. Okay? Again, this is with a pinch of salt because this is applicable only when y dot is 0. So if the system's y dot was not 0, and there I might see that U might still exceed U max by some value in some cases. But as a rule of thumb, you will more or less be guiding it to be somewhere close to U max. That is the idea behind the process. Okay, so now if we want the system's poles to be at a certain location, we can think of a spring mass damper system, and I think this is where maybe there was slight confusion. Okay, let me try to put a page here. Okay, so a typical spring mass damper system will be given by mx double dot plus d times x dot plus k times x is equal to 0, right? So that will be a typical spring mass damper system. And in this case, we are actually going to be looking at some control input u. So in this case, generally it is f. I can also call it u for the sake of convenience. Then we know that for this system, if I take a Laplace transform, I'll get m times s square plus b times s plus k times x of s is equal to u of s. So if I specify u of x of s by u of s as the transfer function for the system, this simply becomes ms square plus ps plus k. A typical way to write down the system is in terms of what we call in a standardized form. So we can write this equation of motion in a standardized form, which is given by 2 times zeta omega n x dot plus omega n square x is equal to some control input u. Notice that this control input is now a scaled factor of the original control input. So I can call that, rather I'll simply call that f so as to make a distinction between them. Okay. So u here will be nothing but f divided by m. Okay. And similarly, we know that these quantities which you get, the natural frequency of the system will be k divided by m, and zeta is the damping ratio. In a standardized form, if I perform the same steps all over again, you can see that the response of the system or the transfer function of the system is given by 2 zeta omega n s plus omega n squared. Everybody with me so far? Now, if we want to look at where are the poles of this system, or where does this transfer function become infinite, that is where resonance will happen. And as long as those points where the resonance is happening is in the left half complex plane of S plane, then we know that the system is more or less stable. That is the primary idea behind it. So where does this become infinite? I can take s square plus 2 zeta omega n s plus omega n square equal to 0, and this is a quadratic equation whose roots will be given by plus or minus square root of omega n times 1 minus zeta square, and there will be a g. Okay, so whenever zeta is lying between 0 and 1, we know that the roots of this equation will be two complex conjugates. So if I plot them in the complex plane, you will see that their real part will be given by minus zeta omega n, and the imaginary part will be omega n square root of minus zeta square, which is also the damped natural frequency of the system. Okay, which is the damped frequency of the system. Okay, so the idea now being that if I want to say that let's place my poles at a specific point, then I know that my existing transfer function, which looks like this, should have some similarity with the transfer function for the spring mass damper system. If these two transfer functions look the same and they have the same coefficients, then I can say that the poles of those transfer functions are located at these locations in the complex plane. Okay, so the idea is I am specifying where the poles should be in the complex plane, and then back calculating what should be zeta and omega n, and then trying to compute the gain values kp and kd such that my system now resembles that spring mass damper system. Okay, so my points of the pole, the location of the poles in the S plane eventually determines what should be my Kp and Kd. That is why it's called a pole placement algorithm. At the end of the day, by doing this process, we are ensuring that the closed loop system's poles are at a desired location which we choose. Everybody following me?
Sir, your voice, I think, became a little feeble.
Oh, I am not audible?
Yeah, the sound became...
When?
Yeah, now it is okay.
Okay. All right. So the idea again is that if I know the location of the poles where I want to place them in the S plane, I want to figure out the values of Kp and Kd such that the system's closed loop behavior exhibits poles at the location which I chose. Okay. That is the idea at the end of the day. Okay. And that will help me characterize the system's response. Okay. Now, typically what happens is that as a control engineer, people will come to you and say, I want to specify certain characteristics of the system. So let us say they'll come and say, the moment I apply the rudder, I want the turn to happen in so much time. Okay, I want this turn rate to stabilize in so much time. Or they may say that once I apply the rudder, from a zero rudder angle, what is the maximum overshoot that I'm seeing in my heading angle? I do not want to see an extensive amount of overshoot in my heading or in my turn rate. So there can be some specifications made in this regard. So based on those specifications, you will basically figure out how far on the left side should the poles be such that these characteristics are matched, such that these characteristics can be met. And that part we are not discussing in this course, but was discussed in your maneuvering and control course. Once we know where the location of the poles are in the complex plane, now the question becomes what should be Kp and Kd so that I can eventually drive the system to that location. And that's the idea which we were trying to take a look at. Okay. All right. So it is easy to see actually if we do the comparison between this system and what we saw before in the spring mass damper system. You can see that here A1 plus B0 times Kd must be equal to 2 zeta omega n, and A0 plus B0 times Kp must be equal to omega n square. Now, since Kp itself is chosen in terms of this so-called design parameter Ey max, I can write this as A0 plus B0 times U max divided by E max is equal to omega n square. Or in other words, I can find my omega n, which corresponds to this, by this equation. Notice here that by changing this tunable parameter Ey, I am essentially affecting a change in omega n, or I am basically affecting a change in how fast the system responds. Okay, the higher the value of omega n, the faster it will respond. The lower the value of omega n, that much slower the system will respond. Okay. One care one has to take here is you don't want this omega n to be too high as well. It should at least be lesser than how fast our rudder can respond. There is no point in asking our system to respond faster than our rudder actually can respond. So let us say we are on a typical ship. The rudder can at max change at about 2.5 degrees per second speed. But I can't command my control system to suddenly produce 10 degrees per second. Even though I may ask it to do that, we know that it will not be able to do it. So it's a bad design in that sense. So typically you want this omega n to be as high as possible, but should be lesser than how fast your rudder can operate. Okay, all right. Now, once we know the value of omega n, we can actually put this into the second equation and we can figure out what is the value of zeta in terms of Kd. So we can write down zeta will become A1 A1 plus B0 times KD divided by 2 times omega n, where omega n is basically coming from here. So this is telling me that if I know what are my gain values, Kp and Kd, I can precisely know what are my damping ratios and the natural frequency. But in reality, the problem is other way around. I know what zeta and omega n are because I know where the poles should be located in the S-plane, and I rather want to express the expressions for Kp and Kd. So we now simply invert these relations to get the value of Kp and Kd. So if I wanted to write Kd, then I would simply write that 2 zeta omega n minus A1 divided by B0. Similarly, Kp would be given by omega n square minus A0 by B0. Okay, so once I know where in the complex plane these poles are going to be located at, I can precisely find out zeta and omega n, and once I know these two, I can compute Kp and Kd. That is the main idea behind the pole placement algorithm. Okay, so I hope that whatever confusion was there yesterday, we have more or less addressed it again, just so that there is some clarity of thought on this. Okay, now what we will do is we'll try to apply this pole placement method for a heading autopilot. So which means that we'll take a Nomotos model for our yaw, and we'll try to see whether we can specify a control law which will allow us to have a specific heading. So remember that the Nomotos equation is given by T r dot plus r is equal to k times delta. Here we are assuming that there is some additional disturbance dr, which is coming due to the influence of ocean currents, wave drift and wind drift. So these are environmental factors which are not allowing my vessel to keep course, or they are trying to perturb my system here and there. Okay. Now, by taking a Laplace transform of this equation, we know that we can express the yaw rate as k by Ts plus 1 times delta plus this so-called disturbance term. Okay, and I'm kind of absorbing that value of Ts plus 1 which I'm dividing by. Okay, so I'll maybe just call this one d, and I'll define dr as d by Ts plus 1. Okay, for the sake of completeness. Okay, so typically k and t are the Nomotos gain and Nomotos time constant. From here we can continue further because we are not really interested in the yaw rate, but we are actually interested in the heading angle, and we know that psi is nothing but psi dot is nothing but r, so therefore psi of s is r divided by s. Okay, so that's why you'll see this extra factor of 1 by s come into the picture once I'm looking at the heading angle psi, where I'm integrating this expression with respect to time, and I'm expressing the entire thing back in the Laplace domain. Now, once I have this transfer function, I can actually make a comparison between that second order system and what I have here. So notice that this also here is a second order system because what I get is k divided by Ts square plus s. Okay, by making a comparison, what I find is B0 will be how much? If I want to make a comparison between this and this, what will be B0? K by T. So K by T will be B0. What will be A1?
1 by T. 1 by T.
1 by T. A1 will be 1 by T. And A0 will be 0. because there is no stiffness in the yaw term. Okay, so we will basically put these values in, and now the idea is we choose the PD control law, where we are trying to specify my rudder angle as a proportional times something proportional times the error, where the error is the difference between the actual heading and the desired heading, and the derivative gain times the side arc. Now, if we specify the maximum rudder angle and leave E psi max as a tunable parameter, this gives us our proportional gain in terms of this parameter E psi max. Then applying the same process as before, you will see this is looking approximately the same formulas as what we saw before. We can figure out what should be the derivative gain and what should be the EY max value for a specified value of natural frequency and a specified value of zeta damping ratio, zeta xi. Okay, by putting these values, I know that I can now make sure that my heading controller tries to track the heading angle psi of t should approach some psi d value using a second order dynamics, which is governed by the poles wherever I wanted to place them. Okay, those poles wherever I wanted to place them give me the values for zeta and omega n, and then I use those to compute my controller gains. All right, this value of omega n that you typically see can be considered as an upper limit of the bandwidth of the closed loop system, and it is generally between 0 and 0.1 hertz. Okay, 0.1 hertz is even 10 seconds. Yeah, maybe. Okay. All right. So if I look at that so-called transfer function, once I look at what is happening in the closed loop system, if I plot it versus frequency, you'll see that it looks something like that. Where omega n being the natural frequency of the system. So it means that, and this value actually starts at 1. Maybe I want to redraw this plot a little bit. All right. So it starts at the value 1, or whatever is the steady state value, which we have, and then it increases to certain value at the natural frequency and decays down as the frequency increases. So you can see that if I am providing this so-called system with a very high frequency signal as an input, then I'll not get anything as the output. So if I specify something at this frequency, let us say, I apply an input signal at that frequency, you can see that the response of the system will be very, very small, right? So when I define the bandwidth, I'm kind of defining the range of the frequencies at which it is allowing whatever input is coming to go out of the system as well. Whereas in the high frequency regime, it's acting like a filter. It's saying that those frequencies will not be allowed to pass through. So bandwidth basically specifies the range of frequencies at which I will expect the filter to pass through its signals. So it's basically telling me what is the width, the notional width of this channel at which it is allowing the signals which are being provided as an input to be transferred to the output of the system. Okay. All right, so that's what I mean by the bandwidth. In fact, I can find specific expressions for the bandwidth, and we'll try to take a look at that in the coming lectures. We'll see that in a few minutes. Okay, notice that we want to limit that natural frequency or the upper limit of that bandwidth so that it does not exceed its maximum value, which is limited by the rudder servo. So we don't want this natural frequency to be very, very high, that once I specify a rudder command, it should at least be slower than the rudder dynamics. Now, because in an ideal situation, you would have probably wanted a system which simply looks like that. Right? Whatever input I give, I simply make sure that I'm tracking the output. But then that physically becomes a challenging portion, because when I have a very, very high frequency signal being provided as an input, that's my pointer. Yeah. So if I have a very high frequency signal, then the time trace of it will look almost like this. Right? And if I want to make sure my rudder actually responds that quickly, it may not actually turn and come back in the time frame that I'm looking at. So it is better to actually filter out those frequencies and make sure that this bandwidth omega m is located at such a location such that it is not causing a lot of wear and tear on my rudder. So you must always try to choose this bandwidth of your controller in such a way that your rudder dynamics at least should be faster than the maximum allowable dynamics from the system, from your closed loop system. Is everybody following me? Yes, no? I'm seeing some few blank faces. Yes, Vallabh, clear? Okay, all right. Okay, now, so far we have included the, what you call, the PD control here, but it is easy to see that when we need the integral action, so we need to do the PID part. So the integral action is needed, especially if we want to compensate for the disturbances. So therefore, when we want to take care of the integral action, it is important first to discuss about what is happening to this so-called error. This error term which we have, psi minus psi d. What is happening to it? Notice that it is a difference between two angles. Right? So it means that whenever I have, let's say, psi has crossed 360 degrees, but psi d has not crossed 360 degrees, then I'll be seeing a sudden quick jump in the value of this E psi, right? Is everybody following me?
No, sir.
See, if let us say that psi d is varying slowly, okay, and I am kind of close to, yeah, so let me see if I can, okay, this is minus pi, and this is pi, okay. All right, so let us say that I'm trying to track a path such that which starts off here and keeps going and then continues back here in some circles. And let's say this is my desired value of psi. Okay, I'm in class right now, later. Okay, so that is my desired value of psi. And let's say the actual value of psi is varying something like that. Okay, so this, let's say this outer fellow is psi. And over time, I'm trying to see that psi should come closer to psi d. Okay. Now the difference between them will keep decreasing technically, but except at this location, except inside this bandwidth. Why? The psi d has made a jump from minus pi to pi, but psi has not made a jump. So suddenly what has happened to the difference between psi and psi d? That error became magnified. Because we are trying to wrap it around a 2 pi, 0 to 2 pi region, right? Minus pi to pi. we have to make sure that whenever we are taking the difference between these angles, it must be the smallest angle which we are taking as the difference. So in order to account for this, we need to make sure, or we need to be clever about the mathematics so that we can specifically map this error to the range minus pi to pi. And we specifically call this as the smallest sine angle. And the idea is that we want to avoid these jumps which are coming into the picture. Now there is a neat way to do that. You can use your modulus functions in order to specifically find out what is the closest angle. And Fawson actually has a neat little MATLAB piece of code which he makes it available to us, that if we pass that angle as the input, it will give me the smallest sine angle as the output. Okay, it's just to make sure that we are consistent here, that I'm mentioning it, that one has to pay specific attention to that. We simply can't take psi minus psi d all the time. Okay. Okay. Now, once we have this so-called difference taken into account, we can now compute our PID control law. So we again see that we have our P part, the D part. Now we have the integral part. And this integral part now has the smallest sine angle, and similarly the proportional part also has the smallest sine angle. This will ensure that there is no jumps in the controller. It will make sure that our controller is doing its job in a smooth manner. All right, so this SSA basically is trying to map a real valued difference in two angles to the range minus pi to pi. And I invite you to take that look. Maybe in the assignment we can introduce you to generate this function on your own and to have a feel for what is going on with it. Okay, now typically when we introduce this integral action, what will happen is that we are now able to compensate for the disturbances and we can achieve a steady state error of 0 more precisely. So that is why the integral action is typically introduced. A rule of thumb is that I want this integrator to be much slower in reaction as compared to my proportional and derivative parts. So what I do is typically I want to choose this integrator gain to be omega by 10 times kp. Then what is happening is it will ensure that my integrator is at least 10 times slower than the natural frequency omega xi of the system. Okay. If our integrator is responding too fast, then it means that it is picking up errors very quickly and then can lead to large overshoots, which is what we looked at the idea of integral wind-up a few lectures ago. Right? So in order to avoid that, we want our integrator dynamics to be slow enough. So a good thought process is that it should be at least 10 times slower than the proportional gain, and we can choose that ki value in this manner to make that happen. Okay, so here what we have, so to summarize what we have done. The idea here is that we have now introduced a PD controller first for tracking the heading value of the ship, and we figured out what should be the gain values specified in terms of wherever I want to place the poles of the system. Okay, and once I know where the poles of the system have to be placed, I can figure out what are my gains, and then I can develop PD control law out of it. Then I can add an integral component to the control law such that the slowly varying integrator can take care of the disturbances which are coming into the system. So in essence, at the end of it, what it will do, it will track my heading angle psi to my desired heading angle which I need. Now that desired heading angle can be coming from one of your guidance laws which we have discussed before. Okay, so either a heading autopilot or a course autopilot can be specifying my desired heading angle, and we are now developing basically a control system which will try to track that desired heading angle. Everybody with me so far? Okay. So what we have seen here does not involve any successive loop closure. We have simply taken a control system, decided where its poles should be, and we have made it track the heading angle. Now we will try to take a look at a second version of this, where we are trying to use our guidance law in terms of the cross-track error between the two waypoints. Okay, so if we are going from one waypoint to the other waypoint, how much far away from the track am I? We want to minimize that track to 0. And we'll see that that can be usually done in the guidance laws that we have developed, right? Line of sight, integral line of sight. These are some of the techniques which we saw before. We'll see how that can work in conjugation with our control system now in order to make sure that we have this successive loop closure that we were talking about relevant to a marine craft. Okay, let's see. So the idea here is we are looking at a path following control system for a marine craft. So the idea is we want to steer a vessel along a desired path with a prescribed speed, and that path is defined in terms of waypoints, and we are specifying the path as straight lines between these waypoints. And it would typically come out of a guidance system as to what should be the desired heading angles and other things should come out of that. But to complete the complete dynamics, let's try to take a look. We know that this cross-track error dynamics is given by u times sine of chi p, where chi p was the angle between the north to the line segment joining the two waypoints, right? So if this point was P and I, and if this point was P and I plus 1, then this angle was, what was the, sorry, this is the angle pi p. Okay, all right. And then if the craft was located at some distance away, with a velocity directed, let's say somewhere like this, then I am looking at the angle between these two fellows, which was given by chi p. So wherever the velocity vector was pointed, between that and the line joining the two waypoints, what is the angle between them? That was the course angle with respect to the path tangential system, right? And that is that angle which will give me the cross-track error dynamics as yp e dot is equal to u times sine of chi p. Now, if the angles are small enough, we are assuming that we are more or less following a straight line path, I can assume this angle to be small enough, which will allow me to make this approximation. Yp e dot is u times chi p. Now, we know that chi p itself is the heading angle plus the so-called crab angle, where the crab angle is nothing but the drift angle, basically. And using our Nomotos model, we can express this, we can replace this fellow using our Nomotos model. Okay, so then what has happened is we have basically expressed our course angle chi in terms of the rudder angle delta plus some external disturbance, which includes an actual external disturbance and the effect that, what is the effect of the crab angle. Okay, so all of that we are lumping together into the so-called new disturbance term, which we are calling di.
What is beta C?
Beta is the crab angle. This is tan inverse of V by U. Okay, so it's basically when I take a vessel, okay, and let us say that this is my north direction, and where the velocity vector is pointed, this angle is chi. That is equal to the heading angle, which is this fellow, plus this angle, which is the crab angle beta c. It's basically the angle between the longitudinal direction of the ship to where the velocity vector of the ship is pointing. Okay, that difference is beta c, which I'm now trying to put it as a disturbance term rather than trying to account for its modeling properly. Okay. Now, this suggests now that we can do our cascading effect. Why? Because we see now that our delta is going to control our chi, which is our course angle. But what we really want is our cross-track error to grow to 0. We don't want to be on the same course angle, but we actually want to be on the path. So therefore, the second aspect of the thing is I want my cross-track error to be 0. And here is where we will use successive loop closure. So we'll first close the loop between the course angle and delta, and then we'll close the second loop between the desired course angle and the cross-track error YPE. So let's see what's happening. So first we choose the inner loop dynamics as a typical PD control. So where I am looking at the difference between the desired course angle and the actual course angle, taking that error, applying a proportional term with respect to that, and then applying a derivative term with respect to psi dot. Okay, this is how I will control my rudder angle in order to make sure that at the end of the day, chi starts tracking chi desired for whatever that desired value is. Okay, once that inside loop is closed, okay, where these gains again can be formulated using our pole placement method, and by now these formulas should somewhat look familiar because we are seeing them over and over again now, right? The same idea is being employed. We specify where the poles of that inner loop system should be, based on which the gains of the controllers will be tuned. Now, once we are ensuring that chi actually tracks chi d, we want to figure out what is happening to this transfer function. How can we ensure that? So in the closed loop dynamic system, you will see that the closed loop course angle chi is given by this transfer function times chi d plus something multiplied by d chi, where that d chi is basically that disturbance term which we had considered before. Okay, so the second order system is now going to try to stabilize the system. So over the range of frequencies of interest to me, I at least want to see that this transfer function is maintaining a value close to 1 over the range of frequencies of interest to me. And then beyond that, I want it to go off to 0. No issues there. Okay, but the downside is when I choose that system to have a value 1 relatively good, it is also allowing the disturbance to have all those values to be passed down, because the transfer function is the same, right? You see that the denominator is the same for both these cases. So if I am allowing the control signal to take in values of certain lower frequencies of rudder oscillations and pass them down into the course angle oscillations, then any low frequency disturbances which are coming due to the wind, wave and currents are also being passed down into the course angle corrections. Now, the idea is, why did I not introduce an integral law? We already talked about that. We could have introduced an integral law here in order to take care of it. But the problem is I want to do the integral at the outer loop scenario so that I don't have two cascading inner loops. Okay, two cascading integrators may pose more challenging problems later on. So that is why I'm trying to put my integrator on the outer loop as compared to the inner loop. So on the inner loop, I'm happy with the fact that yes, there can be some steady state disturbances, but I'll close the loop in the outer side. Okay, so one quick thing to notice here that with the PD control, we cannot cancel out the drift term. This term doesn't go to 0, but we can make its value small, so its effect can be reduced as this value of T by K times Kp is made bigger and bigger. Sorry, is reduced. And in order to reduce that, we can see that as I increase the value of Kp psi higher and higher, this value will become bigger bigger and smaller and smaller, resulting in the disturbance effect to be smaller and smaller. Okay, so a higher gain value will allow me to reduce the effect of the disturbance, but not eliminate it completely. And I have to live with that a little bit. And we will now try to understand what is happening to the outer loop dynamics, which is with respect to the cross-track error, and see that if we can provide the integral law in there in order to compensate for these things. Okay, now our cross-track error was given as u times chi p. So if I take a Laplace transform of that, this is what I get. Correct? IPE becomes u by s times chi p. Now chi p was nothing but chi d minus pi p. So therefore now the idea becomes I want to now drive this fellow using a pi control type, so proportional and an integral control type, such that YPE becomes 0. And then what am I doing there? I'm simply specifying my desired heading angle as pi p minus kp times EY. And if it is only up till this much portion, you can already see that it starts looking like our LOS guidance scheme as long as that kp value is 1 by delta. Everybody with me? It looks very much like our LOS guidance scheme, proportional LOS guidance scheme. Now, in addition, we want to add this integral term so that we can now try to compensate for all those disturbances which were there. And with all of this put together, I can write down. So you notice here that I want to make sure that the error is taken between the actual cross-track error and 0. So which means that I want to make sure that I want to track all my errors in the cross-track direction to 0. But for the purpose of clarity, let us say that I specify this EY as YPE minus some reference value RY. We are choosing that RY as mostly 0 for most of our purposes, but let's say that I choose that value of RY and give it a name. Okay, and then I substitute into this control law into this equation here. So I basically pull this fellow and substitute here. And then I try to take a Laplace transform of it. You should see that the expression for YPE to RY comes out to be what is shown here. Okay. And I'm not going to go through this because it is basic algebra. More or less, you should be able to make sure that this happens. Only thing required is take the Laplace transform after substituting the control law into the YPE dynamics. And you should be able to see that you arrive at this expression for the transfer function between the cross-track error and the regulated value at which I want to drive it. Now, the idea here is I want to make sure that this tracks to 0, or Ry must be equal to 0. So that I can again specify in terms of a pole placement method using this transfer function which is in the denominator. I can specify where the poles of the system should be specified, and then I can specify what should be the Kp and Ki terms which are required for me to achieve that. Now, the idea here is I want that bandwidth separation between the inner loop and the outer loop to be there. Remember, this entire process only works when the inner loop dynamics has a bigger bandwidth and the outer loop dynamics has a smaller bandwidth. So I want to ensure that if the bandwidth of the inner loop is denoted by omega chi and the bandwidth of the outer loop is denoted by omega y, I want this to be at least 5 to 10 times lower than the other one. Okay, that is the primary idea behind the process. So in the end, our control loss block diagram looks somewhat like this. I'm taking the value of my YPE, feeding it back with respect to RY, and that becomes my error term. I take that error term, apply a proportional constant, and I also apply an integral value, add them up, and apply this pi p value in order to make sure, so I'm adding this pi p value in order to make sure that I'm getting my so-called desired heading angle. Okay, so that is what is going to give me the desired heading angle here. Now there was an inside loop which was going on here, which was ensuring that my desired heading angle translates to my actual course angle. The desired course angle translates to my course angle. We already looked at that controller before and tuned its gains accordingly. So therefore that will ensure that my output is actually tracking my input. Now I take that course angle and apply this value of pi p, subtract the value of pi p in order to get the value of this projected angle with respect to the part tangential frame. And that, when I integrate, will actually give me the dynamics of YPE. So that is how the net control loss block diagram looks like. Okay, so in essence, the idea is what we will try to see is we can set up an assignment for you guys to look at the idea that how the internal and the external loops, the inner and the outer loops, have a separation in bandwidth. I'll ask you to tune it such that the dynamics is coming out is proper. We'll also try to see when we don't do that, what funny things can happen. Okay, so we'll try to see that through some of our assignments which will be coming up. All right, so with that, maybe I'll stop for today, and next time we'll discuss about PID pole placement algorithms. Specifically with respect to spring mass damper systems, we'll revisit it once, and then we'll look at non-linear pole placement methods. So far what we have been looking at, the plant has been linear, right? That is why we are able to take this Laplace transforms and deal with it. But what happens in the non-linear case is what we will be trying to look at in the coming lectures. Something interesting which I forgot to mention and none of you stopped me, so I'll go back and take a look here. So remember that when I was discussing about the LOS guidance scheme, I told you that finding this integral gain is quite challenging, right?
We used a y-int term, right?
Correct. So we used a y-int term, which was a nonlinear guidance system, in order to make sure that the integral compensation happens better. We can always do that here as well. Okay, so we can actually try to see what happens in our assignment. We'll try to see between the two of them as to how the performance is with the integral term being specified like this, or the integrator being a little nonlinear. How does that affect the dynamics of the system? Okay, we'll try to see all of that through an assignment. Okay, any other queries before I close down shop today? In that case, let me stop recording.